needs to be satisfied. And I could expand this in the following form. 0 equals a plus b cosine kl plus 2 plus a minus b iota sine kl plus 2, kl over 2. So this is one of the equations that I have at my disposal. So this term must be 0, and so must this term be 0, because this is the imaginary part, and there is neither a real part here nor an imaginary part. So both of these terms have to be 0 at the same time. Now I have two unknowns, a and b. So this one equation is not sufficient. So I write down the other equation which is applicable at this boundary. By the way, these are boundary conditions. These are called boundary conditions. What happens to the wave function at the boundary? The other condition will give you a result which is somewhat similar. And the result would be 0 equals a plus b cosine kl over 2 minus a minus b iota sine kl over 2. Alright? So I have two equations at my disposal. Now, in the previous lecture, I challenged you if you were able to find a and b using these coefficients. And the general consensus was it's not possible. Then you came up with equations for the derivative of the wave function and looked at the boundary conditions, but that is not required at all. In fact, you can use only these two equations to actually find out a and b. Let me describe how this is done. Now, this first part must be 0. This first part must be 0. And both of these parts are identical. So, this equation does not give any new information. This equation is just the same as this equation. The only difference is the minus sign. But we have 0 on the other side of the equation. So, this equation doesn't give any new information at all. So, can we just use equation number 1 and find out what the wave function should be? In fact, yes. This equation has two equations in disguise. One is the equation a plus b cosine kl over 2 is 0. The other equation is a minus b sine kl over 2 is 0. So in reality, we do have two equations. A plus b cosine kl over 2 must be 0. And I would like to emphasize that and means at the same time another equation should be satisfied, and that equation is a minus b sine kl over 2. Now I have to come up with conditions that satisfy both of these equations at the same time, simultaneously. So I come up with different possibilities. The first possibility is, say, a equals b. So if I would like to make this equation 0, this equation has to be 0. Now there are two possibilities. The first possibility is that a equals b. And if a equals b, then this equation is indeed satisfied. And I don't care what this constant is. I don't care, because a equals b, that will enforce this equation to be 0. And this k could be anything. So I enforce a equals b. If a equals b, this is satisfied. And then I would like to satisfy this equation simultaneously. Now since a equals b, this becomes 2a cosine kl over 2. This must equal 0. Now how can this equation be 0? One possibility is that A equals 0. But if A equals 0 and A equals B, then I do not have any wave function to start off with. Alright, so A cannot be 0. If A equals B, then A cannot be equal to 0. Then I have imposed a constraint on KL over 2. The cosine of certain arguments is 0 always, provided KL over 2, the argument of the cosine function is 90 degrees, 270 degrees, or multiples thereof. So if K, this would imply that if A equals B, then KL over 2 must equal pi over 2 or 3 pi over 2 or 5 pi over 2 and so on. So KL must equal pi, 3 pi, 5 pi, 7 pi and so on. So KL equals n pi, where n is odd. Alright? So if A equals B, then I have solutions to both of these equations, and I have imposed the restriction that A equals B. If A equals B, then KL must equal pi, 3 pi, 5 pi, and these conditions together, KA equals B and KL equals multiples of pi, odd multiples of pi, would satisfy the boundary conditions. Alright? So I have exhausted one possibility. The other possibility is, say, A equals minus B. So I look at this equation and I impose the restriction that this equation is satisfied, and it's going to be satisfied always when A equals minus B. If A equals minus B, then this equation is automatically satisfied. But if this equation is satisfied, then I put B equals minus A here. This becomes 2A sine KL over 2. So if A equals minus B, which is my second possibility, then I have imposed certain restrictions on KL over 2. And what are those restrictions? If I look at this equation over here, I will get A minus B, B is equal to minus A, 2A sine of KL over 2 equals 0. But A cannot be equal to 0 now. So this term must be constrained. KL over 2 must have certain values. The sine of 0 degrees or 180 degrees or 360 degrees is 0. So my KL over 2 must be, this must be pi, 2 pi, 3 pi and so on. Which means my KL must be equal to 2 pi, 4 pi, 6 pi, 8 pi. In other words, my KL must be equal to n pi, with n is even. Alright? So KL is 2 pi, 4 pi, 6 pi. If A equals B, my KL equals n pi, where n is odd. And if A equals minus B, my KL equals n pi, where n is even. Yes?
Shouldn't this be 2 and 5?
Well, you could write 2n pi if n is any number. But I'm writing n is even here. What's the third possibility? The third possibility is that A is not equal to B and it's not equal to minus B. Right? So there are only three possibilities. One possibility is A equals B. The other possibility is A equals minus B. The third possibility is that A is neither. Is neither A equals B, neither is it A equals minus B. So the third possibility is A is not equal to B, nor is A equal to minus B. Or let's write A, neither A equals B nor A equals minus B. There are only three possibilities for A and B. Either they are equal, or one is equal to the inverse of the other, or neither of the two conditions. So if you have neither of the two conditions, this becomes some constant C, which is non-zero. Then you have certain restrictions. Sine KL over 2 must be equal to 0. Which means KL over 2 must be equal to pi, 2 pi, 3 pi. But if you put those values of KL over 2 in here, you will never be able to satisfy this equation simultaneously. So this third condition is excluded automatically. So you're only left with two possibilities. Either A equals B or A equals minus B. And if A equals B, then KL is n pi where n is odd. And if A equals minus B, then KL equals n pi where n is even. So now we have found out our coefficients A and B. And our wave function that I've written at the top is has now been executed, which means that my wave function inside the well is, if A equals B, then I can write A, P, I. Now my Kx, K is now equal to n pi over L. So my Kx becomes n pi x over L. So instead of K, I write n pi over L plus B is now equal to A. So I just take A common plus A minus I n pi x over L, where n is odd. And if the if n is even, my wave function is A. Now when n is even, A equals minus B. So my wave function is EI n pi x over L minus E minus I n pi x over L. So now, depending upon whether n is even or odd, I have found the solutions to the Schrodinger equation inside the well. And I can simplify these expressions even further. If I look at what I've written over here, can you tell me from trigonometric identities, what is EI something plus EI minus I something? It's 2 times cosine of this something. So my wave function inside the well, inside the infinite well, is 2 times A cosine of n pi x over L, where if n is odd, and what is EI something minus E minus I something? It's 2 times iota times sine of something. So I get 2 times A I sine of n pi x over L if n is even. Do you understand up to this point? So now I'm using an identity, and the identity that I'm using is that E I theta is cosine theta plus iota sine theta if I add to this e minus I theta, this is cosine theta minus iota sine theta. This gives me 2 cosine theta. That's the identity that I used on the top here, and on the bottom I'm using the identity e I theta minus e minus I theta equals 2 iota sine theta. So using these identities, I've actually determined the wave function inside the well. Now let's try to plot these wave functions and let's try to make sense of what's going on. Now, this is the dawn of a new revelation. A new idea is being given birth to. Something that is at the heart of how nature works. Now what we would like to do is we would like to look at these wave functions. Now are these wave functions real or imaginary? This is real, this is imaginary, but this iota doesn't really matter because it's a global phase. Global phases don't matter. I can put a minus sign here, a plus sign here, it doesn't really matter. So what I would like to do now is the following. I would like to plot these functions. And I don't care about this iota for the time being. Because this is inconsequential, this is just a global phase. Now what values can n take? First question, is n an integer? Yes. What's the minimum value of n? The lowest value of n? 1. Is that even or odd? Odd. So when n equals 1, this is the solution to the Schrodinger equation. This one. So I would like to plot this wave function now. Alright, so if you look here, yes.
जब आपने a minus a is equal to minus b वाले केस में n डिफाइन किया था, सर तब अगर n 0 होता तो भी इक्वेशन सफाई करती थी, स्टैंडर्ड करती थी, तो n 0 भी नहीं हो सकता इस केस में.
If we put n 0, n is even, then sine of 0 is 0. The wave function doesn't exist. Alright?
जहाँ पे हमने n डिफाइन किया वहाँ पे तो n 0 हो सकता है.
हो सकता है, लेकिन then the wave function is just trivial, it doesn't exist. So we would like the particle to actually exist. So we start from n equals 1. Now if I would like to take n equals 1, I would have my attention onto this function here. Because this is valid for odd n's. And 1 is odd. So when n equals 1, the function is 2a cosine pi x over L. Now how do I plot this function onto this graph? Can you plot cosine pi x? So the wave function is now 2a cosine pi x over L. Could you please plot this function onto this graph? Now this is a graph, okay? The wave function is on the vertical axis and this is x. Could you attempt to plot this function? It's a cosine function. What would it look like? Yes, it's a cosine function. So, when x equals 0, this is at its maximum value. When x equals L by 2, so this is L by 2, this becomes pi by 2, cosine of 90 is 0. So it's like a cosine function. Outside this region, the wave function goes to 0. So now we have found out the wave function corresponding to n equals 1. This is the wave function. And this is astoundingly fascinating. I'll tell you the reason in a minute. But let me first of all draw all the wave functions. This is the wave function for n equals 1. Now let me draw the wave function for n equals 2. So this, I'm just drawing the infinite well here. Okay? Now for n equals 2, this equation would apply. Because 2 is even. So my wave function in its mathematical form is going to be given by 2a sine of 2 pi x over L. Now could you please plot this function onto this graph? Could you please attempt doing this question? Forget about this iota, or just plot the real part of this, in other words. You don't have to worry about this iota here. When x equals 0, the function is 0. When x equals L by 2, the function is again 0. When it equals minus L by 2, the function is again 0. When x equals L by 4, this point is L by 4. This is L by 2, this is L by 4, 1/4 of L. So I put L by 4 here, this becomes pi over 2, sine of pi over 2 is 1. So I'm actually plotting a sine function here. This is the wave function for n equals 2. And outside the well, the wave function from the physics of the problem is 0, because we cannot expect that the particle exists in the forbidden region. So now we have plotted the wave function for n equals 2. This corresponds to n equals 1, so I have no harm if I put 1 here, which shows the value of n. There's no harm in doing that. This is sine 2x. This is the value of n. Likewise, I can plot all the wave functions, because now I have the formulas at my disposal. Because this is a plot of this function. Here the wave function is going negative. Can the wave function go negative? Yes, there's no harm in the wave function going negative. Out of the well? Alright, the question that the student asks is, isn't this going outside the well? Well, the well is the well in X. So there's a well means there's a certain region of space in which the particle exists, and that's the region of space. The well is between minus L by 2 and plus L by 2. So the wave function is non-zero inside this region. And when we solve the Schrödinger equation, this is the function that we get. The wave function can indeed be positive or negative. No harm in doing that. So this white line is a graph of the potential energy, and this yellow is a graph of the wave function. Yes?
Sir, for a function to be continuous, the derivative at a point should also be the same. But
I'll explain that. I'll explain that. So now let me draw the wave functions for n equals 1, 2, 3, 4, and a few of those. So I'm going to plot all of them on the same diagram. Okay, so this is the well, this is the forbidden region here, this is the other forbidden region, And I'm just going to draw the wave functions. And I'm going to plot them instead of drawing different diagrams for different wave functions because that will take up a lot of space. I'm just going to stack them on top of this diagram. Okay? So for n equals 1, the wave function looks like this. For n equals 2, the wave function looks like this. For n equals 3, the wave function will be given by this formula, but 2a cosine 3 pi x over L. So, it's for x equals 4, and so on. I can plot all the wave functions because I can plot sine and cosine functions quite easily. Now there are certain observations here. First observation is that on the walls, what's the wave function? 0, always. For all the states, for n equals 2, n equals 3, n equals 4, and so on, whatever the value of n is, there is always a 0 at the walls. So at the node, so these zeros of the wave function are called nodes. The first observation is that we have nodes at the walls. Why do we have nodes at the walls? Why do we have nodes at the walls? Right. So beyond the walls, the wave function has to be 0 because this is the forbidden region. Therefore, at the walls, the wave function must be 0 because the wave function has to be continuous. We cannot have a wave function of this kind. So if this is a wall and abruptly the wave function goes to 0 at the wall, this is impossible. Our wave functions are always continuous. If you would like to keep the energies finite, the wave functions are always continuous. So we observe that whatever the value of n is, there is always a node at the wall. Yes?
So why is it that the waves are always
Because if you have a situation like this, suppose you would like to have a situation like this. In 0 region of space, in a 0 distance, you would like a wave function to abruptly change. Suppose your little heart desires that. In order to do that, what you would like to do is you would like to destructively interfere all waves in this region. Which means that at this region, you would like to have another wave that is joined with this wave that abruptly goes from a maximum to a minimum, like this. And you're squeezing this in an infinitesimally small region. This new wave, which would like the wave to go, which would make the wave go 0 here. Now you're squeezing this new wave into an infinitesimally small region, which means that the wavelength is exceedingly small. Now the wavelength is exceedingly small, p, which is h over lambda, is infinitely large. Now when this p is infinitely large, the energy goes infinitely high. So if you would like to remain sane, and you would like to remain natural, And you're not an omnipotent being, and you're not a supreme being. You would just like to remain a mortal human being. You would like to keep the energies finite. So you would like to keep the energies finite. You cannot have a wave that has infinitesimal or zero wavelength so that you keep the energies same. So the wave function cannot actually be discontinuous. There are no abrupt changes in the wave function. So there must be nodes at the walls. The second requirement, the second observation that you make is that even though there are nodes at the walls, there could be additional nodes in the wave function. For example, at n equals 2, there is a node at the center. For n equals 3, there are additional nodes. There are 2 additional nodes. So for n equals 1, the wave function looks like this. For n equals 2, the wave function looks like this. For n equals 3, the wave function looks like this. For n equals 4, the wave function looks like this. For n equals 5, the wave function looks like this, and so on. So you get more and more wiggles in the wave function as n goes up. The wave function becomes more wiggly. There are more undulations, more turns, positive and negative turns in the wave function as you increase the value of n. So if you increase the value of n, there are more nodes inside the wave function. So n equals 1, how many nodes does it have inside the well? 0. It doesn't have a node. It only has nodes at the well, but all wave functions have nodes at the well. This has 0 nodes. N equals 2 has 1 node. N equals 3 has 2 nodes. So there are n minus 1 additional nodes in the wave function, besides the nodes at the walls. So there are, the second observation you make is that there are n minus 1 nodes in psi n x plus the 2 at the wall. So there are 2 nodes at the walls always. This comes out from the continuity of the wave function. And in addition to those 2 nodes, you have n minus 1 nodes inside the well. In other words, the wave function becomes more and more wiggly as n goes up. There are more undulations in the wave function. Alright. The third observation that you could make easily is what is the slope here? Let's find out the slope of the wave function. The wave function is continuous. But let's look at the slope of the wave function. Here the slope is 0. Here the slope is slanting down, slanting down, slanting down, and here it goes to 0 again. So is there an abrupt change in the slope of the wave function? Yes. The slope of the wave function abruptly changes. And the third and fourth equations that we wrote in the previous lecture, they were incorrect for this infinite well. Because the slope of the wave function can infinitely change if the potential energy goes to infinity. If the potential energy goes to infinity, which is an idealization, which is just an ideal case, the slope of the wave function can abruptly change. And please turn down your mobile phones abruptly. Alright, so the wave function is continuous, but the slope can be discontinuous only if the potential energy goes to infinity. Alright, so this is the third observation. I'm not going to write it down because it's a slightly technical subtlety. Now let's look at this n equals 1. Let's focus our attention on n equals 1 and see what's fascinating about it. So this is my infinite well. The potential energy goes to infinity here in this region, and inside the well, the wave function looks like this. Now this is the wave function. Now, does the wave function have a physical meaning? Well, you need to take the modulus squared of the wave function. That gives you the probability density. Yes.
In that case, would B be 0 because the wave is transmitted?
In which case?
Because the wave, when the wave turns, the wave doesn't come back.
No, it does come back. So, A and B in our original equation. So there is an A here and there is a B here. B is non-zero. So you have a forward propagating wave and you have a backward propagating
There is
wave.
no additional potential after that. So
No, the potential is infinite. Alright, so our wave function is this, right? This is our wave function. Do you all agree with that? Either a plus sign here or a minus sign here, depending upon the value of n. So there is a wave that is moving to the right, and there is a wave that is moving to the left. And when you have waves of this kind, so there is a wave that is propagating to the right, and there is a wave that is propagating to the left. And both of these waves combine to give you this pattern of the wave function. And you all know that such a pattern is also called a standing wave. So the third observation is actually, I forgot, thanks for asking the question, is that we have a standing wave pattern. These are all standing waves. So a wave comes in and it is reflected from the boundary. This is a hard boundary, a hard wall, a hard fence, which is insurmountable for the particle. The particle cannot go beyond it, so it is reflected. Now you have a right propagating wave and a left propagating wave, and both of them interfere to give you a standing wave pattern. And we'll see how does it change with time. We haven't yet included the time factor in. Nevertheless, this is a standing wave, and you have both an A component and a B component. Alright, so now if you look at this wave function, I would like to make physical sense out of it because I'm an experimenter. I would like to find out the question, where can I suppose to find the particle? The first question is, I cannot ask where is the particle because that's a nonsensical question. I can, however, be slightly more modest and ask to myself, if I were to perform an experiment and I were to find out where the particle is located as an outcome of an experiment, what is the probability that my particle is located here, 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 anywhere inside X? Here I know that the particle cannot be found. This is the forbidden region. Here I know that the particle cannot be found. It's the forbidden region. So I would like to find out the probability density. How does the probability density change with space? So I just take this wave function, this one, and take the modulus square of it. So now if I plot the modulus square of this wave function, let me use a different colored chalk for this. Here the modulus square is 0, 0. And the modulus square, of course, is going to be given by, so this wave function is 2a cosine of n pi x over L. Even without looking at this mathematical form, you can just take the square of this function. And if I took the square of this function, looks like this. And mathematically, the square of this function, psi x modulus squared, which gives me the probability density, small p, is going to be given by the square of this, 4 a modulus squared. Now this can be complex. Quantum mechanics is strange, everything can be complex. So, a modulus squared, and just take the square of this. Cosine squared, n is now 1, or n equals 1. So there is, now one would assume that space has gained some regions of space are more special than others. And this is very unusual. Because what's happening here is that if I were to locate the particle in this region, I will take this probability density and integrate from this point to this point. And I will get an area under the curve. And that will give me the probability of locating the particle inside this region. Now this probability is of course higher than this probability. So if I were to take an interval of the same length, of the same width, towards the edge of the well or towards the center of the well, then this probability is larger. So there is not a uniform probability density of locating the particle inside the well. It would like to squeeze away from the walls of the well if it is in the n equals 1 state. If the particle is in the n equals 1 state, the probability density becomes non-uniform. There's higher probability density of locating the particle here. So if you take a narrow strip here and you would like to find the probability near the center, there are more chances that you find the particle in the center of the well rather than at the edges. So now what's happening here? This is quite unusual because there's nothing special about this region. There's nothing special about this region. There's no uniqueness to any point in space. However, the particle would like to cluster, would try to roam about, or the wave function tries to become more prominent in the center of the well, if n equals 1. Alright, so if the particle is in the n equals 1 state, if n equals 1, then there's a higher likelihood of finding the particle in the center. Now if I ask you the question without recourse to the mathematical formula, if I ask you the question, what's the average position of the particle? What would you answer? It's going to be the center of the well. That's the average location of the particle. But there's a higher likelihood that this particle is found towards the center than towards the edges. Now let's look at the n equals 2 ground state. By the way, one nice thing, and this is a good point to introduce this, I have not said anything about A so far. A is totally undetermined up to this point. But I can actually determine A by the normalization condition. What's the probability of locating the particle anywhere inside the well? 1. It has to be somewhere inside the well. No doubt about that. So if I integrate this probability density over the entire length of space, which is effectively integrating only over this region because the particle is not found in the forbidden region, the integral should equal 1. And that will help me determine this A. Let me do that. So this is the process of normalization. Alright, so I've just taken the probability from here, the probability density, which is probability per unit space, and I've integrated over space. What I'm actually doing, I'm taking these points, multiplying this with the length of the space, which is taking the area under this curve. That's what an integral is. So I'm finding the area under this curve. That should be 1. And that's the probability. So if I solve this integral, 4 is a constant, this is of course a constant, 4 a modulus square, cosine square pi x over L is 1 plus cosine of 2 pi x over L over 2. Okay? So instead of cosine square pi x over L, I've written 1 plus cosine 2 pi x over L. Trigonometry. No calculus. So this is 2 A modulus squared, the integral of 1 is, what's the integral of 1? X, limits L by 2 minus L by 2 gives me L, plus, now what's the integral of a cosine function? Sine. So if I take L by 2 here, I get sine 2 pi L by 2, which is sine pi, which is 0. If I put minus L by 2, I get sine minus pi, which is also 0. So the integral of this vanishes. Now this is 1. Which means that my A modulus squared is 1 over 2L. Which means that my A is 1 over 2L under root. Alright? So this is my value of A. Now will this value of A hold for other wave functions for n equals 2, n equals 3, n equals 4 as well? It's going to be the same A for all the wave functions. Because there's nothing special about the A's in the other wave functions. So this is my A, and I can write the n equals 1 ground state, for example, as 2 times this A is this thing, so I get 2 over L cosine pi x over L for the ground state. Now let's look at the n equals 2 state, and let's look at the probability density of the n equals 2 state. Alright, so this is the wave function. Excuse me, still in class. This is the wave function for n equals 2. This wave function is now given by over here. And I can ignore this iota. So this wave function is 2 times A, which is again 2 over L sine of n equals now 2, because I'm talking about the n equals 2 wave function, 2 pi x over L. This is a plot of the wave function. And if I were to take a plot of the modulus squared of the wave function, which is the probability density, the wave function can be negative, and it is indeed negative here. But the probability density has to be positive in normal, rational quantum mechanics. It has to be positive. So if I take the modulus squared of this wave function, what do I obtain? I will get a sine square function. Now, if the particle is in the n equals 2 wave function, then there is 0 probability density near the center. There is very little probability density near the center because there's a node in the wave function at the center. So now, this is strange. There are certain regions inside the well that are trying to exclude the particle. You can perform an experiment and you'll never be able to find a particle at the center and very little probability of locating the particle towards the center of this well. Whereas there will be a higher probability of locating the particle at a distance which is 1/4 of the length from the edge of the well, and a higher probability of locating the particle at a distance which is 1/4 from the other side of the edge. So now there is a certain, this spatial symmetry, the space is now becoming unique. There are certain regions in the space that are becoming unique and others that are becoming less unique. The symmetry or the isotropy of space is being broken. Isotropy means that all points in space are not the same. That's what the probability density is actually telling us. Alright, so let's take a 10-minute break and we'll continue with further discussion.